Hi friends, welcome back to the Swayam course on differential calculus. In this session, we discuss the concepts of curvature, radius of curvature and circle of curvature at a point on the given curve. Consider two curves PA and PB as shown in the figure. From the figure, it can be seen that the curve PA is bending more rapidly than curve PB in the neighborhood of the point P. At the point P, a particle moving along the curve PA has to change its direction much faster than a particle moving along the curve PB. Mathematically, bending of curve means the change of direction of tangents to the curve at a point and is the curvature of the curve at that point. We discuss this concept in detail in this and the coming sessions. Curvature and radius of curvature. Let P be a point on a given curve and let Q be a point very near to P. Two cases arise. The point Q lies to the right of P or to the left of P. We consider the first case, that is, assume the point Q lies to the right of P. We denote the arc between the points P and Q on the curve by arc PQ. By choosing the point Q very near to P, it is possible to have that the bending of the arc PQ is continuously in one direction. Let the tangents at P and Q make angles psi and psi plus delta psi with the positive direction of the x-axis. The angle QTR between the tangents at P and Q is called the angle of contingence of the arc PQ. It can be seen that the angle QTR is equal to delta psi. We define arc length or length of arc between two points on a curve as the distance between the points along the arc. We let the length of the arc measured from a fixed point A to P is S and that from A to Q is S plus delta S. Then length of the arc PQ is equal to delta S. We define the ratio of angle of contingence of the arc PQ by its arc length as the average bending or average curvature of the arc PQ. That is, average curvature of arc PQ is equal to the ratio angle of contingence of arc PQ by length of arc PQ. Hence, here average curvature of arc PQ is equal to delta psi by delta S. Now, we let the point Q approaches P along the curve. Then we denote the right hand limit of the ratio by limit Q approaches P plus average curvature of arc PQ is equal to limit Q approaches P plus of the ratio angle of contingence by length of arc, which is equal to limit delta S approaches 0 plus of the ratio delta psi by delta S. Similarly, if we approach the point P along the curve by moving the point Q that lies to the left of P, we obtain the left hand limit by limit Q approaches P minus of average curvature of arc PQ is equal to limit Q approaches P minus of the ratio angle of contingence by length of arc, which is equal to limit delta S tends to 0 minus of the ratio delta psi by delta S. We assume that the curve and the point P on that curve is chosen in such a way that the above two limits exist and have the same value. The common value denoted by limit delta S approaches 0 of the ratio delta psi by delta S is equal to d psi by ds is called the curvature of the curve at the point P. The Greek letter kappa is used to denote the curvature. As the curvature depends on the point on the curve, we express it as a function the point on the curve. Thus, kappa of P is equal to d psi by ds. curvature of a circle. We are now going to show that the curvature at any point on a circle is a constant, and the constant value is the reciprocal of the radius of the circle. We first note that an arc of a circle is a portion of the circumference of the circle. The length of the arc is simply the length of its portion of the circumference. The letter S is used to represent the arc length. We know that a degree is 1 upon 3/60th of a complete rotation around a circle. Radian is an alternate unit used to measure an angle in trigonometry. Just as it sounds, a radian is based on the radius of a circle. 1 radian is the angle subtended at the center of a circle by an arc that is equal in length to the radius of the circle. In calculus, we prefer radian measure of an angle rather than a degree measure. In a circle, arc measure is the measure of the central angle that intercepts the arc. The measure of the central angle theta in radians is the ratio of the length s of the arc, the angle subtends divided by the radius r of the circle. That is, theta is equal to s by r, which is equal to length of subtended arc by length of radius. Now, to show that the curvature at any point on a circle is a constant, we consider a circle having radius r centered at the origin O of the xy Cartesian plane. Let P and Q be 2 points on the circle, and let the length of arc PQ is given by length of arc PQ is equal to delta S. Let PT and QT prime be tangents at the points P and Q respectively. Also let the meeting point of the tangents PT and QT prime be the point L. Then from the figure we have angle POQ is equal to angle TLQ, which is equal to delta psi. We have noted above that the measure of central angle theta in radians is the ratio of the length s of the arc, the angle subtends divided by the radius r of the circle. That is, theta is equal to s by r, which is equal to length of subtended arc by length of radius. Hence, here angle POQ is equal to length of arc PQ by r. That is, delta psi is equal to delta s by r, which implies delta psi by delta s is equal to 1 by r, a constant which is the reciprocal of the radius r. Hence, this value is unaltered if we apply the limit as delta s tends to 0. This gives kappa of p is equal to d psi by ds is equal to limit delta s approaches 0 of the ratio delta psi by delta s is equal to 1 upon r. Hence, the curvature at any point of a circle is a constant, and the constant value is the reciprocal of the radius of circle. We now discuss the circle of curvature and radius of curvature. The circle of curvature or osculating circle at a point P on a plane curve where kappa of P is different from 0 is the circle in the plane of the curve that satisfies the following conditions. First condition, the circle and the curve has the same tangent at the point P. Second condition, the circle lies toward the concave or inner side of the curve. Third and last condition, the radius of the circle is 1 upon kappa of P. Since we know that curvature of a circle at any point is the reciprocal of its radius, the condition 3 in the definition of the circle of curvature is equivalent to the following statement. The circle of curvature and the curve has the same curvature at the point P. The radius of the circle of curvature at a point P is defined as the radius of curvature of the curve at the point P and is denoted by rho of P. Thus, rho of P is equal to 1 upon kappa of P. Since kappa of P is equal to d psi by ds, the above gives rho of p is equal to ds by d psi. The center of curvature of the curve at p is the center of the circle of curvature. As a special case, we note that if a curve itself is a circle, say C, then at any point P on the circle C, the circle of curvature of the circle C is the circle C itself. We have noted earlier in an example that curvature of the circle at any point is the reciprocal of the radius of the circle. Hence, the radius of the circle of curvature is the reciprocal of the curvature of the circle at the point P. Thus, the radius of curvature of a circle having radius r is given by rho of p is equal to 1 upon kappa of p, which is equal to 1 upon 1 by r, which is equal to r, which is the radius of the circle. Hence, the circle of curvature of the circle C is the circle C itself. A catenary is the curve that a hanging chain or cable assumes under its own weight when supported only at its ends. A catenary curve has a U-like shape, superficially similar in appearance to a parabolic arch, but it is not a parabola. Catenaries and related curves are used in architecture and engineering in the design of bridges and arches. The first mathematical study on the catenary curve was done by English architect Robert Hooke in the 1670s. The equation representing a catenary is given by S is equal to C tan psi, where S is a variable denoting the length of arc AP along the curve from a fixed point A, and psi is also a variable denoting the angle between the tangent at P to the curve and the x-axis. To find the curvature at a point P, we use the formula kappa of P is equal to d psi by ds. Here, ds by d psi is equal to d by d psi of C tan psi, which is equal to C sec square psi. Hence, curvature at any point P of the catenary is kappa of P is equal to d psi by ds, which is equal to 1 upon C sec square psi, and the radius of curvature at any point P is rho of P is equal to 1 upon kappa of P, which is equal to C times sec square psi. In this session, we introduced the concept of curvature, radius of curvature and circle of curvature at a point on the given curve. In this session, we discussed the formulas involving the variables s and psi, where the variable s denotes the length of arc AP along the curve from a fixed point A, and the variable psi denotes the angle between the tangent at P to the curve and the x-axis. In the coming sessions, we will use the formulas discussed in this session to obtain curvature etc. to a point of a curve when the curve is given in any one of the forms: Cartesian equation, parametric equations and polar equations. See you next time. Till then, bye.